We can give a lot of other examples. You can take the set of all integers with less than or equal to. This is a partial ordered set. And the set of all rational numbers with less than or equal to is a poset. Set of all real numbers with less than or equal to is again a poset, where less than or equal to is the usual less than or equal to relation among the numbers. So these are all examples of posets. Now suppose, to get another example, you consider R cross R, the set of all ordered pairs of real numbers. Here we can define an order like this. You take any two elements of, there is one element is x1, y1. Suppose that you take another element x2, y2. Both are elements of R cross R. R cross R or R2. Given any two such ordered pairs of real numbers, we can define a relation like this. That is x1, y1 less than or equal to x2, y2 if x1 is less than or equal to x2 and y1 is less than or equal to That is, one ordered pair will is less than or equal to another ordered pair if and only the first coordinate is less than or equal to the first coordinate and the second coordinate is less than or equal to the second coordinate. This is a partial order because this is reflexive, transitive and also antisymmetric. And since complex numbers are nothing but ordered pairs of real numbers, the same partial order can be defined on complex numbers. But most of the time we will not be using this partial order on the complex numbers because this particular order and the algebraic operations of the complex numbers are not having any compatibility. That is why we are not using this order, or actually in the case of complex numbers there is no sensible order you can give which makes it a ordered field. Another remark I would like to mention is that I defined a partial order as a relation less than or equal to. Some people may have some problem with this notation. Why? Because this less than or equal to is something familiar to you. That is less than or equal to, this is actually the relation which you use among numbers. But here I define less than or equal to is a relation on a set X satisfying reflexivity, transitivity and antisymmetry. This is just a relation. I am just using this notation, that's all. So this less than or equal to is may not be the same the less than or equal to you are familiar with. So, and actually you need not use the same symbol, you can use any symbol. You can say R is a partial order if it is R, a relation on X is a partial order if it is reflexive, antisymmetric and transitive. But it's convention that this notation is used. And sometimes some people will be having some problem with using this notation. If you belong to that category, you can do anything. You can use a similar a symbol like this, and you use this symbol for the abstract partial order, and for your concrete one you can use the. Some people may be having such a feeling, or you can use this symbol. But most of the people usually use this symbol for the abstract, for an arbitrary partial order or pre-order. And if we need more than one partial orders on the same set, we can use these three different symbols together. Now, suppose x less than or equal to is a poset. And suppose A and B are elements of x. Then it can happen that both these statements are false. A not less than or equal to B and B not less than or equal to B. For example, you take your set x your set as A is equal to AB and x as the power set of A. Then you take two sets, singleton A and singleton B. Then singleton A is not a subset of singleton B, and singleton B is also not a subset of singleton A. That is, in a partially ordered set, if you take two elements, it may not be these two elements may not be comparable. That is, it can happen that A not less than or equal to B and B not less than or equal to A. Such things can happen. And actually, I gave another example. A set of all positive integers with the partial order divides. You take two integers, say 2 and 3. 2 does not divide 3 and 3 does not divide 2. So they are not comparable. Whereas 2 divides 4, 3 divides 6. 2 divides 6 also. But 2 and 3 are not comparable in the sense that 2 does not divide 3 and 3 does not. So that is why this structure is called partial order, in the sense that it is not complete or total. But in the case of some partial order sets, can happen that any two elements are comparable. For example, you take the set of all real numbers with the usual less than or equal to. Then given any two real numbers A and B, either A is less than or equal to B or B is less than or equal to A. So in the case of that some partially ordered sets, any two elements are comparable. So for such let x less than or equal to be a poset, then less than or equal to is a linear order if for every AB element of x, A is less than or equal to B or we say that if any of these two relations are satisfied, then we say that A is comparable. A and B are comparable. There is x less than or equal to is a linear order if is a linearly, this less than or equal to is a linear order if any two elements are comparable. That is, for any two elements A and B, either A is less than or equal to B or B is less than or equal to A. And we, in that case, we also say that this is a linearly ordered set. There is a linearly ordered set is an ordered pair x less than or equal to, where x is a set and less than or equal to is a linear order. Instead of linear order, some people use simple order or simply ordered set. Some people use the word totally order, a total order and totally ordered set. Or some people even use ordered set and order without any adjective. So depending on the book you are referring to, you can see all these various terminologies. Some people call it linear order, some simple order, some call it total order, or even order. And correspondingly, linearly ordered set, simply ordered set, totally ordered set, and ordered set. A typical example is the set of all real numbers with less than or equal to, or the set of all integers with less than or equal to, the set of all positive integers with less than or equal to, or the set of all rational numbers with less than or equal to. All these are examples of linearly ordered sets. And sometimes a linearly ordered set is also called a chain. Sometimes a linearly ordered set is also called a chain. Now, suppose that x less than or equal to is a poset. Poset is an abbreviation for partially ordered set. Now, we can define another relation, that is for xy element of x, we define x less than y if x less than or equal to y and x not equal to y. X is a set and less than or equal to is a partial order on x. Therefore, x less than or equal to is a partially ordered set or a poset. Then for any two elements x of x and y of x, we can define a relation x less than y if x is less than or equal to y and x not equal to y. So this is called x is less than y. And also we can define x is greater than or equal to y if y is less than or equal to x. You can write x greater than or equal to y if y is less than or equal to x. This one is the inverse of the other relation. Or you can say x greater than y if y is less than x. Some people also use relations like this. X not less than y. That is, you write less than or equal to, then cut. This means x is not less than or equal to y. That is, the statement x less than or equal to y is not true. And you can also use symbols like this, x not less than y, and x. So x not greater than y, etc. X not greater than or equal to y. These symbols, these relations can also be defined in any partial order set. Now, so if you take a partial ordered set x less than or equal to, and if you take the relation less than, this relation is having certain properties. One property is that for every x element of x, x is not less than x. That is, no element is related to itself under this relation. This is usually called the irreflexivity. We say that this relation is irreflexive. Irreflexive means no element is related to itself. We defined another property called reflexivity. Reflexive means every element is related to itself. For example, less than or equal to is a reflexive relation. But strictly less than is an irreflexive relation in the sense that no element is less than itself. So that is one property. Another property is that this is also transitive. That is, for every x, y, z in x, x less than y and y less than z implies x less than z. That is, the relation less than is irreflexive and also transitive. There is one assertion. Now, conversely, suppose x is a set and less than is a relation on that set, which is with the two properties, that is, less than is irreflexive and less than is transitive. Suppose we are given a relation on x. Now, from this relation we can define another relation as follows. We can define a relation less than or equal to as follows. How? X less than or equal to y if x is less than y or x is equal to y. Confusion varade. അതായത് എക്സ് എന്നുള്ളൊരു സെറ്റിൽ ലെസ് ദാൻ ഓർ ഈക്വൽ ടു എന്നുള്ള ഒരു റിലേഷൻ ഉണ്ടെങ്കിൽ അത് ഉപയോഗിച്ചുകൊണ്ട് ലെസ് ദാൻ എന്നുള്ള റിലേഷൻ എങ്ങനെ ഡിഫൈൻ ചെയ്യാൻ നമ്മൾ ഡിഫൈൻ ചെയ്യുന്നത്. ഇനി സിറ്റുവേഷൻ മാറ്റാം. സപ്പോസ് എക്സ് ഉള്ള സെറ്റിൽ ലെസ് ദാൻ എന്ന് പറഞ്ഞിട്ടൊരു റിലേഷൻ ഉണ്ടെന്ന് വിചാരിക്കുക. അങ്ങനെയാണെങ്കിൽ ലെസ് ദാൻ ഓർ ഈക്വൽ ടു എന്നുള്ള റിലേഷൻ ഇങ്ങനെ ഡിഫൈൻ ചെയ്യാൻ പറ്റും. ആൻഡ് വൺസ് യു സ്റ്റാർട്ട് വിത്ത് എ ഇർറിഫ്ലെക്സീവ് ട്രാൻസിറ്റീവ് റിലേഷൻ ലെസ് ദാൻ ലൈക്ക് ദിസ് റിലേഷൻ വിൽ ബിക്കം റിഫ്ലെക്സീവ്, antisymmetric and transitive. Or you can say that this relation is a partial order. A relation less than which is irreflexive and transitive is also having a name. Some people call it strict partial order. Or some people call it quasi order. This quasi order may have some other meaning in some other textbooks. This mathematical terminology are not very standard. So you'll have to look at the book which you are referring. Depending on that, some slight difference of meaning. So an irreflexive transitive relation is also called a strict partial order or quasi order. So what we observed here is that on a set X, if there is a partial order, corresponding to that we can define a quasi order, which is irreflexive and transitive. And on the conversely, suppose on a set we are having a quasi order, that is a irreflexive transitive relation. Using that we can define a reflexive, antisymmetric and transitive relation, that is a partial order. So in other words, given a partial order there is a quasi order in it, and given a quasi order in it there is a partial order also. So you can, instead of defining a partial order set as a set with a partial order on it, that you can also define it as a set with a strict partial order or quasi order. And in some books that approach is also used, but we are not using that approach. But of course note that a quasi order will not be a partial order and a partial order will not be a quasi order. Now we have to define some concepts in partial order sets. So for that let x less than or equal to be a poset. In some posets, there will be an element which is less than or equal to every other element. For example, you take a set A and you take the power set of A. That is the set of all subsets of A. Now, empty set is an element here with the property that empty set is a subset of every subset of A. So that means this is less than or equal to every set. Such an element is called the smallest element. And for example, if you take the set of all real numbers between 0 and 1, the closed interval 0 and 0, 1, here 0 is the smallest element. So such a thing can be defined in a partial order set. So suppose x less than or equal to be a poset. Then an element of x is called called a smallest element of x if A is less than or equal to x for every x element. Such an element is called a smallest element. Some partial ordered set may not contain a smallest element. For example, you take the set of all real numbers. This contains no smallest element. Why? Given any real number x, x minus 1 is a real number less than that. So there is no smallest real number. There is no smallest integer. There is no smallest rational number. But there is a smallest element in the set of positive integers. If you take the set of all positive integers with here 1 is the smallest element because 1 is less than or equal to every positive integer. So some partial order set may contain a smallest element, some partial order set may not contain a smallest element. But if a smallest element exists, that is unique. Suppose there are two smallest elements. Suppose A1 is a smallest element and A2 is a smallest element. Then it is clear that A1 is less than or equal to A2. Why? Because A1 is a smallest element. And similarly, you can also prove that A2 is less than or equal to A1 because A2 is a smallest element, therefore it is less than or equal to every other element including A1, therefore A2 is less than or equal to A1. A1 less than or equal to A2 and A2 less than or equal to A1 together gives A1 is equal to A2. What we proved is that the smallest element, if it exists, is unique. So there cannot be two different smallest elements in a partial order set. Now, similarly, we can define a largest element. Some people call the smallest element, some people call it the first element. Some people are calling the smallest element also another name, first element. Some people are calling it minimum element. So how to define suppose you take a B, an element B of x, then it is called, a B is called a largest element if x is less than or equal to B for every x. This is the definition. An element, suppose that x less than or equal to B a poset and B is an element of x. Then we say that B is called a largest element of x if x is less than or equal to B for every x. That is, every element is less than or equal to B. Then we say that B is a largest. A partial ordered set may contain a largest element, may not contain a largest element. The set of all real numbers, the set of all real numbers with usual order does not contain a largest. If you take the power set of a set A with set inclusion, there is a subset of as a partial order. This is a partial order set. This here A is the largest element because every subset of A is contained in A. You take the set of all positive integers with the partial order divides. This is a power set. Here 1 is the smallest element in the sense that 1 divides every other integer. But there is no largest element. There exists no integer which is divided by every positive integer. Such a integer does not exist. So there is no largest element. If you take the set of all positive integers with usual order, this contains the smallest element 1 but no largest element. If you take the closed interval 0, 1, here 0 is the smallest element, 1 is the largest element. And largest element, if it exists, is unique. And sometimes largest element is also called the last element. Largest element is also called the last element. Or sometimes maximum element. The set of all integers with usual order does not contain a smallest element, does not contain a largest element. You can also define the smallest element for a subset of a poset. Suppose x less than or equal to is a poset, and suppose A is a subset of x, and suppose A is an element of A. Then we can write A is a smallest element of A. If A is less than or equal to x for every x element of A. Similarly, largest element can be defined. That is, B is an element of A. B is a largest element if x is less than or equal to B for every x element. And of course, the smallest element and the largest element of a subset, if it exists, is unique. A subset of a partial ordered set need not have a largest element, need not have a smallest element. So that this can be defined for any subset of a partial ordered set. Now, suppose X is a partial ordered set. X with a less than or equal to, suppose this is a partial ordered set. Then, if Y is a subset of X, then we can also consider Y also as a poset. How? What is this less than or equal to? Less than or equal to is a partial order on X. That means it's a relation on X. That is, this is a subset of X cross X. That means less than or equal to is actually the collection of some ordered pairs of elements of X. Now, you can take the intersection of this with a Y cross Y. You can take the intersection means you are taking those ordered pairs of less than or equal to which are for which both the coordinates are in y. This will be a subset of y cross y. Actually, this is obtained from this relation, but of course this is a subset of y cross y, means this relation. Suppose I am denoting this relation as, say, less than or equal to dash. This will be a subset of y cross y, means this is a relation on y, and this relation is called the relation induced from this relation. And once this relation is a partial order, this relation is also a partial order on y. And with this partial order, y can also be considered as a poset. Or in other words, subset of any partial ordered set can also be considered as a poset with essentially the same relation. The only difference is that this is restricted to y cross y. That is, we are taking only those ordered pairs in less than or equal to with both the first coordinate and the second coordinate in y. So actually there is a restriction of this relation to y. That is, in order to define a partial order on y, it is suffices to know whether two elements of y are related or not. That information is also given by the original partial order less than or equal to 1x. In this sense, we can say that a subset of a partial ordered set is also a partial ordered set. So, a subset of any partial ordered set can also be treated as a partial ordered set. For example, we are having real m with less than or equal to is a partial ordered set, and it subsets the set of set of rational numbers, set of positive real numbers, set of negative real numbers, set of all integers, set of all positive integers, set of all negative integers. All these are subsets of, and they are also endowed with the essentially the same relation, less than or equal to the usual order. And we usually use the same notation also for these relations. But strictly speaking, you'll have to use different notation. That is, suppose you take real line. In real line, there is a relation less than or equal to. What is this actually? This less than or equal to is actually a subset of R cross R. That is, this less than or equal to contains all ordered pairs xy of real numbers where x is less than or equal to y. Now, you take the subset z, that is set of all integers. There also we use the same notation for the less than or equal to, but this contains only those ordered pairs xy where x and y are integers. So, theoretically speaking, these two are two different sets, but we usually give the same notation for both. But strictly speaking, they are different. But for the convenience of that, we use the same notation, as we do in, say, C++. Even if you define a function for, let's say, modulus function, absolute value function for the complex numbers, absolute value for the real numbers, or absolute value function for the integers. In some programming languages, these three are three different functions and given different names. Whereas in C++, usually we give the same name. So the mathematical practice is that all these relations are given the same symbolic representation, but from the set theoretic point of view, they are to be treated as different. മാത്തമാറ്റിക്സിൽ അങ്ങനെയാണ്. ചില സമയത്ത് നമ്മൾ ചില കാര്യങ്ങളൊക്കെ ഒരു റിഗറിന് വേണ്ടിയിട്ട് വളരെ കണിശമായിട്ടെല്ലാം ഡിഫൈൻ ചെയ്യുകയൊക്കെ ചെയ്യും. പക്ഷേ പ്രായോഗിക കാര്യങ്ങളിലേക്ക് വരുമ്പോൾ നമ്മൾ ചിലപ്പോൾ ഇതുപോലെ ചില കള്ളത്തരങ്ങളൊക്കെ ചെയ്തിട്ട് അത് നമ്മളൊരു അണ്ടർസ്റ്റാൻഡിങ് വെച്ചുകൊണ്ട് നമ്മൾ ചെയ്യുന്നതാണ്. അതുകൊണ്ട് പ്രശ്നം ഉണ്ടാവില്ല. ബട്ട് എല്ലാ കാര്യങ്ങളും ഡിഫൈൻ ചെയ്യുമ്പം എല്ലാം വളരെ റിഗ്രസ് ആയിട്ട് വളരെ കൃത്യമായിട്ട് ചെയ്യണം. അപ്പോൾ അത് നമ്മൾ വളരെ കൃത്യമായിട്ട് ചെയ്യും. പക്ഷേ പ്രായോഗിക തലത്തിലേക്ക് വരുമ്പം നമ്മൾ ചിലപ്പോൾ സ്റ്റൈലൊക്കെ മാറ്റും. ഇപ്പോൾ ഉദാഹരണമായിട്ട് ഇപ്പോൾ ഒരു റിലേഷൻ എന്ന് പറഞ്ഞാൽ എന്താ ശരിക്കും ഒരു റിലേഷൻ എന്ന് പറഞ്ഞാൽ എന്താണ്? ഇറ്റ്സ് എ കളക്ഷൻ ഓഫ് ആൾ ഓർഡേഡ് പെയർസ്. അപ്പോൾ എന്താ ശരിക്കും ഇപ്പോൾ 1 ഈസ് ലെസ് ദാൻ ഓർ ഈക്വൽ ടു 2 എന്ന് പറയുന്നതിന് പകരം ശരിക്കും എന്താ പറയേണ്ടത്? 1 ലെസ് ദാൻ ഓർ ഈക്വൽ ടു 2 എന്ന് പറയുന്നതിൻ്റെ അർത്ഥം എന്താ ശരിക്കും? ഓർഡേഡ് പെയർ 1 2 ഈസ് ആൻ എലമെൻറ്റ് ഓഫ് ലെസ് ദാൻ ഓർ ഈക്വൽ ടു എന്നല്ല പറയേണ്ടത്. പക്ഷെ ഇത് വളരെ ഓക്വേർഡ് അല്ല എങ്ങനെയാണെന്ന്. അതുപോലെ എന്താ പറയുക, ഇപ്പോൾ y ഈസ് ഈക്വൽ ടു സൈൻ എക്സ് നമ്മൾ സാധാരണ എഴുതല്ലോ. പക്ഷെ ശരിക്കും സ്ട്രിക്ട്ലി സ്പീക്കിംഗ് എന്താണ്? സൈൻ എന്നുള്ളതൊരു ഫംഗ്ഷനാണ്. ഫംഗ്ഷൻ എന്ന് പറഞ്ഞാൽ ഒരു റിലേഷനാണ്. റിലേഷൻ ഈസ് എ കളക്ഷൻ ഓഫ് ഓർഡേഡ് പെയർസ്. അപ്പോൾ ശരിക്കും ഇവിടെ എന്താ സ്ഥിതി? ദ ഓർഡേഡ് പെയർ എക്സ് വൈ ഈസ് ആൻ എലമെന്റ് ഓഫ് ദ ഫംഗ്ഷൻ സൈൻ. അങ്ങനെയല്ല ശരിക്കും കൃത്യ ഡെഫിനിഷൻ വെച്ച് പറയുകയാണെങ്കിൽ ഇങ്ങനെയല്ല പറയേണ്ടത്. പക്ഷെ ആരെങ്കിലും ഇങ്ങനെ പറയാറുണ്ടോ? അറിയില്ല. അപ്പം പ്രായോഗിക കാര്യങ്ങളിൽ നമ്മൾ ചിലപ്പം മാറ്റങ്ങളൊക്കെ വരുന്നത്. പക്ഷേ നമ്മൾ അതൊന്നും കുഴപ്പമില്ല. കാരണം എന്താ, നമ്മൾ ഇതാണ് നമ്മൾ ഉദ്ദേശിക്കുന്നത് നമ്മളിങ്ങനെ എഴുതുകയാണെങ്കിൽ അതുകൊണ്ട് കുഴപ്പമില്ല. സോ മാത്തമാറ്റിക്സിൽ ഇതുപോലുള്ള ചില വിധികളൊക്കെ ഉപയോഗിക്കേണ്ടി വരും. അല്ലെങ്കിൽ കുഴപ്പമില്ല. എല്ലാം നമ്മൾ വളരെ റിഗർ ഉപയോഗിച്ചിട്ട് തന്നെ റിഗറസ് ആയിട്ടുള്ള നൊട്ടേഷൻസ് നമ്മൾ ചില ഉപയോഗിക്കുകയാണെങ്കിൽ അവസാനം ഇത് വളരെ കോംപ്ലക്സ് ആവും. അവസാനം ആൾക്കാർക്ക് വായിക്കാൻ മനസ്സിലാവും. അതായത് അല്ലെങ്കിൽ പ്രായോഗികമായിട്ട് വളരെ കോംപ്ലിക്കേറ്റ് ആവും നൊട്ടേഷൻ. സോ നമുക്ക് ഈ റിഗറും വേണം, അതേ അവസരത്തിൽ കാര്യങ്ങൾ മനസ്സിലാവും വേണം. അതുകൊണ്ട് പലപ്പോഴും നമ്മളൊരു കോംപ്രമൈസ് ഇങ്ങനത്തെ കാര്യങ്ങൾ ചെയ്യാറുണ്ട്. ഇപ്പോൾ റസലിൻ്റെ പ്രിൻസിപ്പിയ മാത്തമാറ്റിക്കൊക്കെ നോക്കുകയാണെങ്കിൽ അവിടെയൊക്കെ വളരെ കൃത്യമായിട്ട് തന്നെ കാര്യങ്ങൾ ചെയ്യുന്നുണ്ടായി കേട്ടോ. പക്ഷെ അത് പ്രായോഗികമായിട്ടുള്ള ഒരു സാധാരണ സ്റ്റുഡൻസിന് വേണ്ടിയുള്ള ഒരു ടെക്സ്റ്റ് ബുക്കിൽ അങ്ങനെ ചെയ്യാൻ പറ്റില്ല. കാരണം അങ്ങനെ ചെയ്ത് കഴിഞ്ഞാൽ കുഴപ്പമില്ല, ആൾക്കാർക്ക് കാര്യങ്ങൾ മനസ്സിലാവില്ല. സോ ഇവിടെ ഒരു കോംപ്രമൈസ് വേണം. അതായത് ഈ റിഗറും വേണം, അതേ അവസരത്തിൽ കാര്യങ്ങൾ മനസ്സിലാവാൻ എളുപ്പവും വേണം. അത് മാത്രമല്ല കുറച്ച് ചുരുക്കി ബ്രേവിറ്റിയും കുറച്ച് ആവശ്യം. അപ്പോൾ ഇത് നമ്മൾ ചില സമയത്ത് വളരെ ചെറിയ കോംപ്രമൈസുകൾ നടത്താറുണ്ട്. പക്ഷെ അതുകൊണ്ടൊന്നും കുഴപ്പമുണ്ടാവില്ല. കാരണം നമ്മൾ മനസ്സിലാക്കിക്കൊണ്ട് എഴുതുവാണെങ്കിൽ കുഴപ്പമുണ്ടാവില്ല.